But this is the iron-based molecule that I want to talk about is ferrate. And I already mentioned that very nice introduction. Muchas gracias again, Pedro, or Dr. Professor. I'm sorry I'm saying my first name, but next slide. So here, yeah. So just one more time, I'm from University of Miami, Florida. So this is where we are in Florida, and which we completed 100 years. So we complete 100 years of this university. And it's a good part that I just joined this university after 100 years. So I just joined recently. And is a member of Association of American Universities. It is a big deal. Why I call big deal? Out of, let's say, 4,000 universities in America, only 62 universities are part of this membership. So it's hard to get this membership. And it's hard to maintain this membership. So be a member of this is a big deal. And we have, of course, many sports and titles, but we have Aerosol Science and Technology Center. And there are many, here is 5 Academy members. So this National Academy member to become is also a prestige over this one. And I just mentioned that I recently joined, but we have small department relatively and how that is progressing here. So this is, and we focus on environmental, chemical, and materials. And we have that many undergraduate and 4 master students. So my task is given, tough task for me, that they make a coordinator for master program. So that means I need to recruit students. And it's not easy task. And so if you are interested in our master program, and then please talk to me. The beauty of, I tell how I sell this program, once you finish this program, you have very good chance to get into PhD in our university or our department. And why it is interesting to do PhD, because PhD is free. Free in the sense you don't need to pay tuition, and we give you the money. Right now, the rate is $41,000 per year that will be paid to our students. And that is this decent sport. And so if you're interested in master program and maybe in PhD, and then please talk to me afterwards. So here is the, as it's a ferrate that I want to talk is about this molecule, which is, I think, is solve the problem of challenges in achieving the water treatment, okay? We have many pollutants in the water, starting with pesticide, PPCP, that is pharmaceutical and personal care products. We have industrial chemicals like PFAS these days, and some toxins there. And these are in concentration very low. Those are in micromolar or nanomolar concentration, okay? And then, but those are in presence of other ions and organic matter, okay? And those are in millimolar or higher concentration. So your pollutants are in basically very low concentration, at least 3 order magnitude lower compared to other major ions and organic matter. So whatever technique you use to treat them, like advanced oxidation processes, they produce like primary radicals. So radical, instead of reacting with pollutants, react with these ones. So how you're going to treat the water? If the produced radicals you're trying to use, they are not reacting with your targeted contaminants. So this is a real problem. And that's why people work in the lab with one chemicals, like previous talk, whatever Spanish I understood, you do one chemical, one metal, and then it's ready to publish because in the lab. Okay. Same thing, people do one chemical and they try to treat in only buffer solution, but when they go to real water, it doesn't work. And this is the real reason. And you can see reaction is very fast with these major ions. Of course, even reaction is fast with your contaminants, but still is 3 order magnitude lower concentration. And even you use some other radicals, these produce, but they react with very fast with oxygen. Again, you cannot have a solution or water treated without oxygen. So you're basically AOPs, most of the time, they are failing to treat the water. Okay? I just, sometime I make some strong statement just to challenge, okay? So you can challenge me because I want to learn too from all of you, okay? So to my knowledge, how you can treat something which is reacting so fast with the major ions, which you don't want to remove, but it is reacting with the majors, but not with the targeted contaminants, okay? So to me, solution is, again, this is a biased strong opinion, lies in metal, high valent metal ions. Probably in your school science classes, you always read about ferrous and ferric ion. But here I am talking about iron in higher oxidation state, 4, 5, and 6. Okay? And they can target the contaminants because they are not attacking with these ones. They are forming complex with this thing, not they're reacting with it. And that's the beauty. And so in nutshell, or very simple, the resistant matrix components, means high valent you can use and enhance their reactivity. I'll explain a little later what that means. Even this presence of major ones, they enhance the reactivity of these species. This is an advantage compared to removal by the AOP radicals. And I'll give some examples. And I want to take advantage of that too. And so it can do multi-mode actions. That means it can perform oxidation, reduction, coagulation, disfaction in just one chemical. So that's, I think, is the solution. And at the end, I'll also give some issue in treating the water. People spend a lot of time to use AOPs rightfully, okay, because we want to use to clean the water. But really, we need oxidation all the time. Maybe some chemical reduction, like PFAS. Oxidation doesn't work. But we have trained students and researchers, scientists in AOPs. So they just use these methods to remove contaminants. So we need maybe advanced redox processes too. More scientists trained in that one. So I'll start with very basic things now. What is the iron, which I am very fascinating about it? These exist in different oxidation state. Iron rod is D8 electrons. So I'm testing your freshman chemistry now, okay? And when we becomes ferrous ion, that means we have taken 2 electrons out. Ferric ion, we have taken 3 electrons out. And these are naturally present. But if you take 4 electrons out, become ferrate 4. And if you take 5, becomes D3, ferrate 5. And if you take 6 electrons, become ferrate 6. So we have taken a lot of electrons out from this iron metal. So think this way. If you haven't heard this argument before in my talk, if you have no Dorino in pocket, you had the Nero, and somebody's taking your money out. How do you feel? Not happy. Right? So I say, don't attack me. If you're not happy, attack the pollutants and get those electrons back. That means you can get your money back from pollutants. Once they get the money back from pollutants, that means they are destroying the pollutants. So that's the trick. So here I have written also that this is active, Ferrate 6 is active, but more active from 6 is 4 and then 5. So 4 and 5 are really more active than 6. If something I cannot take care, pollutants, doesn't destroy that pollutant, I have a hope with 4 and 5. And in short term, this Ferrate 6 can do, as just I mentioned, many action of Ferrate. It can do oxidation, remove antibiotics, disinfection, and bacteria, virus, and then it's also remove metals. That's coagulation. And my focus is here, but let me give some example of these ones. Like here, a coagulation example is removing arsenic. And beauty of this removing arsenic is really go to the inside the lattice of iron oxide, so you can really release back. This one. Here's the example of virus in coronavirus. It can remove. That removal, it can kill it very quickly. There you can see here, this is this here, some other technique, but 6 is really, you don't see anymore, this coronavirus on the surface. So you can use them in hospitals, these kind of things. And I always, whenever I give talk, I always mention 1 or 2 sentences. If you don't have to go hospital, don't go, because people acquire infections in hospitals because they are not clean. But this molecule, I see the future that it can take care of some bacteria and virus, which is very difficult using chlorine, because chlorine is there for a long time. They resist now. Bacteria, virus, they're very smart. They resist disinfection. And here is somebody was mentioning yesterday to me using pesticides very much in this area, because agriculture is done by pesticides. So we have a lot of pesticides. So why don't we use some other friendly things? So I'm developing a technology where you can basically clean this vegetables and fruits using this molecule. And it is a big deal. You can see after this one here, treatment, bacteria, E. coli is gone and it looks fresh. It has a big meaning, because that means you can keep in store for a longer time. More shelf life is longer once you treat with this liquid. And as I just mentioned, you can use even for fish or vegetables, and possibly, I haven't tested this for meat, because if you see, there's so many recalls are happening regular basis. So you can use this solution to clean it up. And you can destroy toxins, because at least in Florida, we have red tide. So there's some toxins. So you can destroy some toxins. You can destroy even other kind of toxins, which is cylindropromopsin, which give headache. The bottom line is showing these 2 slides. You can use this molecule to destroy toxins. You can remove metals too. And let me focus on the antibiotics, because that is very big deal, or antibiotics in the environment. They are creating antibiotic-resistant bacteria and genes. And this will be, according to World Health Organizations, one of the biggest crisis of the century. Why that is the case? Because I just mentioned in hospitals, same thing, antibiotics don't work. They're getting very much used to. And we are not producing any new antibiotics. It's not profitable. So one day crisis will come, government will spend money like just coronavirus and solve that problem. But right now we have a problem. We are not producing new antibiotics. So how antibiotics enter into our water? One is, as I said, is people use a lot of antibiotics. Overused actually, because we are living longer and you go to doctor, I'm not feeling good, doctor feel uncomfortable, okay, you have more antibiotics, may you feel better. So we are consuming a lot of antibiotics. But those are then 60% come out from your urine. And that go to the environment. There's no metabolize. But actually, we always say human consumption, but most of antibiotics actually also used for farming. Even seafood farming and other livestock, there's coming a lot of antibiotics because nobody wants to get sued, at least in the US. So they use a lot of antibiotics to make sure no bacteria, virus. And I'm sure in Mexico also use a lot. So I got this project proposed, why don't we clean the urine before it go to water? Something is diluted. Once you go to water, it get diluted. Then it's difficult to clean based on the kinetics. So I'll just move on these ones. But we tested, this is some other, not my work, but we have also tested in the wastewater treatment plant. Okay, to see if we can remove antibiotics and pharmaceutical byproducts, so many in the wastewater treatment plant using this molecule. And these are two different kind of plant. And what do you see here? I see good news and not so good news. I don't use bad news word, not so good news, okay? And what is good news? This is a removal percentage, and these are different compounds or contaminants. Most of them you can remove 100%. Okay? And not so good news, some you cannot remove. And I like to get the title, I work a lot on iron, right? I want to get the title, I'm the real Iron Man. Okay? And how I can get this title? If I remove these ones too to make it 100%. Right? And then question is how to do it. Okay? And here is the answer. As I said very early on, here is the 6 I'm using. Why not I use 4 and 5? Which is much faster reactive than 6. So I can take 6, go this way, reduce it, or I can take 2 or 3 and form 4 and 5. And you can see this is cyanide, how fast the reactivity with cyanide. This one here. So the bottom line is, something you are not able to remove this one, use 4 and 5 to remove this one here. And other thing in this thinking we learn that once you reduce form 4 and 5, and if these ligands are already present there, what the ligand I'm calling here? The major ions or organics, very beginning problem. Then it can form complex. And reactivity of this one is different from here. So once I know this, I am ready to manipulate things now. And we have found reactivity with ligands is much faster, or at least faster than this one. So that means it is helping. Those ligands which interfere in the treatment of advanced oxidation, it is really helping here. And I will show some example. So let me start with the simple thing first. Just learn from this one and see what happened. So back to reminding one more time, something Ferrate 6 can do in minutes, but 4 and 5 can do in seconds and milliseconds. And I start calling this as activated Ferrate technology. You're using Ferrate, but you're activating it now to make it use of 4 and 5. And how to make it, that I'll show you some example. Here is, you can use RN3. RN3 is always used because you combine RN6 with RN3. Just we learn. And you can see here examples. If you have no RN3, you have 20% removal. Once you combine with this RN3, then it's 100%, or at least it's increasing for some other ones. And RN3 is cheap. That means you can use even minerals to enhance the activity. And even other ions, those are present, positive ions, calcium, aluminum, these ones, they can also enhance it, but RN3 is showing much more reactivity in terms of activation. So this is one way of activating is just use RN3. What about other one? Simple one. Use a minerals, manganese oxides, minerals. And you can see here it's a little bit complicated because, but this is not my work, but you can see here, manganese oxide is not removing it. The once you combine with manganese oxide and RN6 is really enhancing it. So using RN6 and minerals, you are activating Ferrate to make it activated Ferrate, and you can remove micropollutants faster and with more efficiency. What is the other example? Silica. Silica is sand, kind of, right? Just use combined with this. And then you can increase, see, this is around 60% and get 100% when you combine RN6 with silica. So these are simple things you can do to activate Ferrate 6. So basically, I gave the example here so far, just take a reductant or at least behave reductant and use this here. But this situation, where does that situation exist? Okay. Here is the situation exists in urine. Urine has these many ions, inorganic ions and some organics. Okay. And it has carbonate, it has ammonia. And what we learn in the lab, once we have carbonate in water, the reactivity is becoming faster. And if you have ammonia, it's also becoming faster. So now we are start using natural ions. And that's why when you see the title of my presentation, I start writing now, harnessing the natural ions to enhance the activity. So the reason is, again, because carbonate and ammonia, they form complex with this. And that has higher reactivity than no complex around. And that's why we are enhancing the removal and activity of this. Okay, just to go back to just to remind here, this, there are organics present too there in urine. And what are these ones? as you can see, so we start doing experiment with the organics too. And this what we learned from this, uric acid, creatinine, and chitinine. We tried this ones and see what they do. And what we learn, these ones, they don't do anything much. But the moment we have this chitinine, is showing some enhancement for most of the pharmaceuticals removal. And so this is very interesting. Urine already have those things, and if you use ferrate, we can remove pharmaceuticals in water or in urine directly. And why that is the case, only thing I can tell right now is it has a ring and nitrogen there. To me, it has a meaning with some vision. And then we also say, let's make healthy water too. What about amino acids? We combine RN6 with amino acids. And we learn about these pharmaceuticals that most of amino acids, they don't do much. For the moment we have proline, which has again nitrogen and ring, then you can see the enhancement of the removal. So these ligands, we can use it to improve the chemistry to basically enhance the removal of micropollutants. And then we did with what about natural organic matter, which is big problem which is everywhere, and we don't know much about it, but they always interfere in the removal of micropollutants. And in our case, what we learn that first thing is, what is natural organic matter? We learn that it is basically enhancing it. Okay? And this year or last year, this thing was actually unexpected, that organic matter is enhancing it. Because so far everybody's saying is with AOPs, it's decreasing it. But our system is showing ferrate is increasing it. And when I wrote the paper, I was still doubtfully I will be able to explain this. But fortunately, someone in the committee who decide about the price of this, I published this here, recognized this thing. And that's why they gave this, Prince Sultan bin Abdul Aziz International Prize for Water. Is considered is big deal about this prize. It's big. In prestige wise is big, and what is other can be big? Money. They give you money. Okay, they really give money. But there were other people who helped me for this research to achieve this so far so many years. So I share that money with them too. There are other three. One from Czech Republic, one from US, two from US. So I equally share the money with them. But this is nice to get this award. So back to reasoning now, why this is happening, okay? So I looked the structure of organic matter which people propose. And I understood nothing from this structure. So complicated, right? But one thing as a chemist, I was trained as a chemist, I looked some functional groups. So I start adding different organics into my system. And what I found that phenolic group or phenolic group on organic matter, that is influencing the activity here. So their phenolic groups are here on the organic matter, react with the RN6, producing 5 and this radical. And remember, I keep saying RN5 is important. And then I needed some evidence. I ran this organic EPR, showed that yes, radical forms. Whether RN5 forms or not, I don't know. And nobody has found it either. So tomorrow I'm flying to Stanford from here. They have nice SLAC instrument, synchrotron, and I'll try this experiment to really find out RN5 is exist or not. So I blame the phenolic group. Then I did many experiment phenolic contents for two antibiotics, trimethoprim and sulfamethoxazole. From many places in Florida, I tested different organic matter. And you can see there is a removal percentage enhancement, at least decent linear relationship the moment you increase the phenolic content. And here is also for SMX is also increasing. So largely responsible is phenolic content in this one here that can increase the removal percentage. So just to summarize, 4 and 5 can enhance it. 4 can do in 10 minutes, 5 can do in seconds. And so then it can also apply to bacteria and viruses, the same chemistry. And again, my goal is saving lives, even one life. And now I'm taking this chemistry, whatever I learned through this simple molecule, how we can create this maybe catalyst. Because we learn enough. Can we create some kind of catalyst which can do itself everything? So single atom is the one, how we can create high valent metal ions and this one. So right now it's just review it and we publish this one, Chemical Society Review. We are very happy about this one. So I show in every presentation because it has very high impact factor. And also microplastic and nanoplastic is also a hot topic. So we have written the review or commentary on saying nanoplastics are potentially more dangerous than microplastic. When you write dangerous, people pay attention and you get high citations. Okay? And so our goal is right now how we can collect these ones using some porous materials. For why they are toxic, you can and behavior, you can read about these two reviews. But we want to collect them. And what to do after collections. Okay. Again, we have learned enough chemistry. Can we convert this plastic after collection into some value-added products? Okay, so that's the other goal that we have. But right now we haven't done any work. So we want to collect microplastic and nanoplastic, and then use chemistry of these high valent metals to convert into value-added products. And we want to use to maybe the light in this process to produce these ones. Okay? And it's always good to say solar fuel because you can convert maybe microplastic. People are doing this work. I'm not the new one here. They are saying we can produce some methanol from the plastics. And last few slides, I want to talk about PFAS, just 3 slides or 4 slides. PFAS is a very big topic in US and now is also in other countries because they are there. Once they are there, they are not going anywhere. Reason is very simple because once they form, these are the kind of example. This CF bond, they say CF bond, because they are stable. That's why they have many applications that you see in consumer products. There are many applications. But suddenly now they have found they are highly toxic, very, very low levels. There's, and now I think US is going a little bit back in terms of monitoring, but European is going forward with these things. About monitoring, and then is saying there, you can see here, it's really, many studies have come recently, they're showing is pregnant woman and all those things is really nasty and nasty, okay? And now, and what is the solution? One solution is people all talk rightfully and they're working very nicely. From the water, you just remove it. That's adsorption, physical phenomena. You can use the filter, you can do adsorbent, that way, activated carbon. You just remove it. But what to do with that one after removal? You just concentrate it. You need to destruction of those ones. And what is the problem with these ones? In terms of removal. First thing is people try to do by oxidation. CF bond is you cannot oxidize easily. You need reduction. And what are the reductant? Electron, hydrogen electron, or sulfide radicals. But instead of, they react with very low concentration of PFAS consumed by oxygen. So you cannot have water, anoxic water, to remove something. Of course, you have many papers already published showing that. Now, if you remove oxygen, it's working very nicely. This hydrogen electron and sulfide. But in reality, when you go to reality, very fast reaction with oxygen, which is hundreds of micromolar to 50, around 50 to 50 micromolar in water. So, but we tried this, I don't know if you heard this one, definitely you heard, metal organic framework, which got the Nobel Prize this year, metal organic framework. And now you can see why it got the metal organic framework prize, because it can absorb gases, it can take the water out from the air. It has many applications. So we have titanium-based MOF we took and put with PFAS, this one, perfluorooctanoic acid, and use the light. And what we found, yes, you can degrade PFOA. And this one was very interesting, at least for me, it was interesting. For organic chemist or hardcore chemist, it was probably a piece of cake. For my one interesting thing I found, it does produce electron. That electron creates some radical immediately. And then it weakens the bond, CF bond. Then OH radical, OAPs are ready to take over. Take over means it's ready to degrade the radical now. It can take the fluoride out. So you can degrade these ones. And it has no effect from oxygen. I still don't know why it has, I have some hypothesis why it is degrading, but oxygen has no effect. Means you can achieve this even in presence of oxygen. So now I just writing proposals. When I go back after California trip, I'm going to submit the proposal to understand what is happening here. Because in next meeting, you're going to ask, does it matter if organic matter is around or ions around? Does it still work? Okay. I cannot show you the data, but we have tried already there, and it works even better, like the other one. Again, I don't know why it works better, But if you have organic matter around, it works better. So my story still continues. So what my goal is, how to enhancing the international collaboration to solve many world problems for water. And I'm very much against focus on public health, security, and some energy. And I want to create this very healthy water where we have a glass of water, you put lime there. The lime also enhances the activity of ferrate because it has ascorbic acid, and that helps. So you have tasty water too. Little bit iron will not hurt because people have iron deficiency. So I want to take the rural community, this molecule, maybe as a tablet, you put the tablet there. People have chlorine tablets too, and just put there, and you save a lot of money just because people don't have to go hospitals, pathogens everywhere, diarrhea. You spend so much money in many, many developing countries, and rural community too. And this funding from this one is National Science Foundations and Department of Agriculture, some Army and environmental, and many colleagues, student, postdoc, nationally and internationally. So I'm here just to speak, hablo, but they are the one who's doing mucho trabajo, okay? Okay, but it's nice, I'm lucky and blessed. And this is my mentor. I just saw him last year, but I need to visit him since I came back from Germany. And why I was in Germany, because this Humboldt Research Award, and Antonio told me it's prestigious one. So I feel even better. Okay. And this is my host who hosting me this to do research on, and somebody has to nominate you. Some of you, if you can apply as a student, Humboldt Fellowships, but research awards, they say it's different category. But you can, as a postdoc or this one, or your friends are there, or someone, you can apply for this. But you need a host. So he's my host. He is one of the best atmospheric chemists in the world. So he has Tropos Lab, and this one is, so he was the host, and I'm trying to learn, can we, in the atmosphere, do this high valent iron exist too? That's the hypothesis. And I do think somebody told 20, 30 years ago, and then everybody forgot about it. But now if they forgot or they found it's not there, that's why they forgot or nobody cared. I don't know the answer. So I want to find the answer. Nobody cared because they found and didn't publish it, or it is really important or very difficult to do it. So I want to do it. And interesting thing is this is the Director General who they do very formal ceremony, like they do in Nobel Prize. They have very expert come, tell your name, no spelling mistake, nothing. And then at the end of your visit, the President of Germany invites you to his house and shake hand with each one over there. I don't have that photo because I was ready to take photo, but other professor came and blocked my view. So I need to get the prize to get shake hand with him. And why not? Here is my journey, muchas gracias, to Mexico. I started my journey in Mexico many, many years ago. And Felipe was the one who invited me, his Marine School in UNAM in Mexico City. I traveled one time to publish this thing and to Mexico City. And Judith, you're here, right? This is Judith. And then I went to Veracruz. This is Veracruz. The previous meetings. So 90s to I'm still keep coming, that I'm trying to convey. And very honored to have with Pedro, and this ambassador of India in Mexico that time. and just somebody told me. And I like to, again, muchas gracias to Antonio. The reason is that it's Antonio, right? Reason is he converted this young student try to learn and make a great scientist. Judith here now, she's running one of the organizer of this meeting. You already see everyone. So muchas gracias also, Antonio, for training to her. And now she's my sister. So muchas gracias. With this, I think I close my talk with these beautiful pictures. Thank you, listening. And you're very welcome to ask questions.
Hi, thank you very much for your presentation. Have you tried to make comparisons of your compounds with common organometallic iron compound?
Okay. You means organic metallic compounds like big organic ligands around, right?
Yes.
That you meant. Yeah, people are working, if I'm understood correctly, people are working on this because iron and big bulky organic ligands, they represent kind of metal enzyme system in our body. And for those are mostly, I did not work myself, but I was the literature this year so I can learn because they are not soluble in water, most of them. So that's why I did not work with them because it's better to work with simple iron and oxygen rather than add the bulky molecule with it. So I think this is a disadvantage to work on those ones. Unless I'm learning from catalyst, I can create some catalyst. That means I'm not using those ones. But I'm afraid of these organics will be attacked by these high valent metal species too. Okay.
Thank you for your interesting presentation. I have just a couple of questions.
Please.
The first is regarding these high oxidation states of iron. Well, we know that iron 2 and iron 3 are not toxic, but what about iron 6 and iron 5?
So iron 6, of course, this is disinfectant, so it's toxic, but I'm not suggesting toxic to whom, okay? The moment you put in water, it will go to 3.
Yeah, but you mentioned that, okay, if you spray vegetables with this iron...
Yeah, so, yeah, that is nothing big damage is happening or any damage is happening. And in contrast, at least whatever we tested, spinach, you see the photo of the spinach,
yeah,
which I think we are very close to get the patent. Spinach get fresher. It doesn't get destroyed, the spinach, because we did only few seconds. We dip it and took it out. And few seconds get fresher. And it's actually is better than what we had before adding.
yeah,
but need to control. If you leave it there, it destroy it.
No, well, I was thinking about human consumption of...
Oh, as I said, is once you put the spinach, this is our thinking is you take it out, right? As I said, in surfaces of those ones, it immediately convert to iron 3, which you can wash off. Okay, but we haven't. If you want to food consumption, you need to do many, many tests before you declare food is safe for human consumption. So, but we don't expect that is the case because iron 3 is not, unless high level creates some phantom chemistry in your body, then it's a problem. But other than that, I think it's not a problem. But we don't have the test. Yes. More questions?
Yeah. Can I have another question? Yeah.
Go.
Okay. The other is about the, removal of contaminants, especially regarding the wastewater treatment plants. Well, you mentioned that oxidation is not effective, destroying some contaminants. Which this is something I'm surprised because, oxidation processes are a common process to, at least for natural organic matter. So, do you know what, I mean, is any physicochemical explanation behind, well, the reason why these chemicals are not destroyed, for example, by UV radiation? And then you have to go for reduction, which is what you are working at.
Yeah. So I think it's AOPs, if they actually somehow didn't realize that only a few years ago. Now I see this titanium dioxide. Some journal came, so much work came out for several decades. New journals started, but you don't see comparatively much use in real environment, except control environment, Switzerland, maybe in Spain somewhere they are using in the solar things. And organic matter, because OH radical. Basically, AOPs are based on OH radical or sulfur radical. They all react with organic matter. So some places, what they are doing is they are using, again, activated carbon to remove the organic matter first before applying the AOPs or ozonation. So that's the way they are trying to do that one. Then you have organic matter full of with activated carbon. Okay. Yes, please.
Thank you for your presentation. I have a little question. What is the viability to escalate this process? Because when in some process it can be expensive to do like the contamination of 100 or 1,000 of liters of water. How viable is to escalate this process?
The scaling of this one.
Yes.
No, this is in still process. It's not done yet. Okay. And that's why I think one thing is fairly for young, increasing words is that you have challenges. Okay. But same time, this to take the lab stuff and finding chemistry to commercialize it, innovation, and that's separate story. Okay. So only thing left in this case is to manufacturing in large scale so we can upscale it. Then it will work. But in the lab, taking the same wastewater, as I said, this one and some other one, it works. So that has commercial part is actually missing, or hopefully I'll be around. I want to see before I move on. I don't know where. Yes. So that's the short answer.
I don't speak English, but
you can speak in Spanish and they can translate.
Okay, I'm writing my question and this.
Please, muchas gracias.
Thank you. Is the thinking of ocean water, the increase of CO2 and the consequence acidification, the oxidation, it's promote the oxidation and reduction of heavy metal as iron and pesticides?
Let's see question. Can you repeat? Sorry, I didn't understand the question. Anybody else can explain the question, then I will be better to address.
Okay. Pensando en la acidificación del océano, del CO2 y la captura del CO2 por parte del océano y esta actividad que al menos entendí que el oxígeno causaba una reducción de los plaguicidas y los metales pesados como el fierro. O cómo puede estar afectando la producción de CO2 y la acidificación del océano al ser un sitio donde se capturan estos tipos de contaminantes.
This is not about ferrate, right? It's as you are asking how CO2 is going to affect the ocean chemistry, right? It's not about ferrate, right? I can relate to ferrate that more CO2 produce more carbonate, so my ferrate will work better. Okay? But in terms of CO2 is creating some acidity that you're saying, and that is kind of hard data showing that, okay? And example, so CO2 is increasing the acidity. I think scientific data we have shown that. And I can tell my experience in Florida, if you go to Keys in Florida, they have nice boat. Like here, they take a boat and show the fish. They show the coral reef. And when I was a student in late 80s, I visited that place. Beautiful, beautiful. But now I go, I don't see that much beautiful. It's bleached actually. That happened 2 years ago. I went, I was disappointed. So because those coral reefs are calcium carbonate species, and acidity can dissolve those ones. So acidity is there. No, you can ask for lunch because they need to go for lunch.
Hi, I like English a lot. I only speak a few words. It's better in Spanish, okay?
Okay.
En 1850, en el norte de Europa, se enfermaron las papas por una bacteria. Eso fue en 1850. Y se murió más de 1 millón de personas por que no había que comer. Hoy el mundo, por producir alimentos, utiliza químicos y agroquímicos y ya lo inorgánico está donde quiera. Por eso en alimentos, en medicamentos, por donde quiera está y nos estamos enfermando de cáncer. ¿Qué va a pasar con ese aceleramiento de la humanidad por producir alimentos y medicamentos y todo está contaminado? ¿Qué futuro nos espera a esta generación que estamos viviendo?
So what the question is, what is the expectation if we keep increasing the pesticides and those ones? Medicines. Okay, it's like anything else, means all over the world. For example, DDT was banned in USA, but you can still get in Mexico. So border areas, you can still find DDT, like in Texas, South Texas, you can still find the people smuggle there because DDT works good, great. But these are things are there. Another problem is, I think, water scarcity or sustainability. Groundwater, we are abusing it a lot. It's going lower and lower. And that means we are concentrating those contaminants. And so this problem will keep becoming worse, actually. So solution is use the solar energy, and because people are not going to change habits, looks like. People still drive big cars, and we don't want to change our habits or lifestyle. So these problems, as in a short one, people keep using more pesticides. Nobody wants to get sued. Nobody wants to get sick. We keep driving more and more from creating more carbon dioxide. We need to find some solution somewhere which can adapt the lifestyle too. So that what Patricia is saying this in her introduction, how to, sorry, I said Dr. Patricia, not Paddy. That was, she was telling us, please careful, you need to find some solution. And that what I think is a very good question, carbon dioxide. So carbon dioxide is very interesting. Only lately it has become topic for me. And 2 papers, if you're interested in EST, I wrote a perspective, environmental science, which will come online soon, what carbonate can do, okay, to the reactions. Another review is coming on carbon dioxide, produce carbon dioxide radical. And that can do it. Hopefully it will get accepted soon. It's under revision. So I'm going to submit by tomorrow, approaching last day. So these are real issues. We need to go out of box and think about it. And hopefully this meeting will bring that solution. That's why we are gathered here. Nice, beautiful place. Muchas gracias. Thank you.
Yo tengo una pregunta.
I have a last question.
Please. Please.
No? Okay. How your research impact in the society? Just that's my question.
How my research?
Impact in the society.
Okay, this is very good question. And this society, for example, I gave example of disinfection because I have a patent just for hospitals, how to clean the surfaces in the hospital, because they have a MRSA and some Clostridium difficile, which is very difficult by chlorine or wipes to clean it. But this molecule, ferrate in liquid, it can do the damage. So it affects the human health that way. And remove the metals, remove the toxins, remove the pharmaceuticals, that's other angle of human health effect or humans. And now I'm moving is how we can use, I'm going to how these molecules can be used further to help the society. Actually, I have published a paper, didn't get the attention yet. Other solution of carbon dioxide, other solution is to create hydrogen gas from the water itself. I think that's the future, to water splitting. And this molecule is going to do it. It split the water splitting very nicely, but it does in acid medium. But recently we are showed with acid medium, you can do it, but it's not good, right? To acid. So we have done in neutral pH to show that using a catalyst based on ruthenium and ferrate, which can do the water splitting at neutral pH, or mild alkaline medium, we can achieve that thing. So it has effect on energy, it has water, it has a food angle and public angle. So water, food, energy nexus, and public health. This ferrate molecule contribute to all these four impacts, basically, which society needs. That was your question? Okay.
Thank you.
Bravo.